Hello everybody, welcome to the second session of the Matrix Algebra with me. So in this session we are going to discuss a little about the inverse matrix and the determinant and different properties how to solve a system of equations. So without wasting time, let's go into it. Now, what is a matrix inverse? Let's recall the number is the inverse of a number in the area of numbers. Let's say we are gonna solve the equation 2x equal to 6. What we're doing here is that we multiply the both sides of the equations with 1 over 2 to solve the equations. And finally, we are gonna get 1 over 2 times 2x is equal to 1 over 2 times 6. And then we say that this is gonna be 1 and this is gonna be x equal to 3. The same as here we have in the matrix. So if we have two number x and y is equal to 1, then we say y or x is the inverse of y. Right? Now, do we have the inverse of a matrix also? The answer is yes. But how do we define it? As we discussed, 1 is a special number in the area of numbers, right? Why? Because if you multiply 1 with any number, you are going to get the same number without any change. But as I told you, in matrix environment, instead of 1, we use identity matrix, which was, depending on the size, it was a diagonal matrix having 1 on the diagonal, for example, and 0 anywhere else. What was the property of this diagonal matrix? It was that if you multiply I with any matrix, you are going to get the matrix itself. And this is going to be the inverse. Also, you are going to get the matrix itself. So now, according to this definition, the inverse of a matrix, if A times B is equal to I, then we say that the B is the inverse of A. Right? Because the multiplication of the A with its inverse is equal to I. So now the question is how we can find A minus 1. In order to find the A minus 1, we need to first have some definitions. First definition that we need to know is the determinant. Right? The determinant of a matrix A, how we define it? I explain it with an example. Let's say that the matrix A is a 2 by 2, 2, 3, 4, 5 matrix, which is 2 by 2. Right? And now we want to know what is the determinant of A. It's simple. For a 2 by 2 matrix, you get the main diagonals and you multiply them 2 times 5 minus, you take the minor diagonal and then you multiply 3 by 4, and the result is going to be 10 minus 12, which is minus 2. This is the determinant, how we calculate the determinant of a 2 by 2 matrix. But now the question is, what if we have a 3 by 3 matrix? how we can define and find the determinant. That's the questions. So now, if we have a 3 by 3 or higher order matrix, in order to find the determinant, we need to have a definition. First, definition is cofactor matrix. The cofactor matrix is a matrix that would define it based on the matrix A. I don't want to use any kind of complicated mathematical equations to define the cofactor matrix. I define it by an example. Let's say we have the matrix A, which is a 3 by 3 matrix. Let's say 1, 3, 2, 4, 5, 6, 8, 7, and 9. This is a 3 by 3 matrix. And now the cofactor of A, where normally we show the cofactor with the theta or anything you want. We say theta of A, which means cofactor of matrix A. Okay, so this cofactor have the same size of the matrix A, so it's going to be 3 by 3. 1, 2, 3, and also here. Okay, so it's a 3 by 3 matrix. So now the first one, the first element of the matrix, which is this one, is the first row and the first column. So now you do like this. You come to the first row and first column of the matrix A, which is 1. And you delete, you put a line and hold the row and the column of this number. This is the first, it means the first column and the first, right, column and row. So what is remaining there? It's a 2 by 2 matrix. Put the matrix here and make its determinant. 5, 6, 7, and 9. Now I'm going to the other element, which is here. The first row and second column. I go to the first row, this is the first row, and the second column, which is this one, so this element of position of this. Again, I do the same. I delete the row and the column. What is remaining is this one and this one. I write it here. 4, 6, 8, and 9. Now, what we can do in here, you need to be careful. You need to sum the row and column. For example, for this element, one row and the first column, first row, 1 plus 1, 2. 2 is an even number, so you put a plus. For this one, 1 plus 2, second column is 3. 3 is an odd number, you put a minus. So, I guess you understand what we do here. You put plus for the element that the summation of row and column is even, and you put a minus if the summation is odd number. If you continue to do this one, you will get the matrix like this. The theta would be 5, 6, 7, 9, minus 4, 6, 8, 9, and I don't want to write the other cases. It's going to be the same. This is a 2 by 2 determinant. Each element is a 2 by 2 determinant, which we know how to calculate it. I told you just before. So if you calculate these ones and write all those, you are going to have the matrix, for example, the cofactor matrix for this matrix, for the matrix A or B is equal to 3, 12, minus 12, minus 13, minus 7, 17, 8, 2, and minus 7. This is the cofactor matrix of matrix A. Now, how we can find and determine the determinant, how we can calculate it. For this one, it's very easy when you find the cofactor matrix. Write the cofactor matrix. On the bottom of that, write the original matrix, the A. It was 1, 3, 2, 4, 5, 6, 8, 7, and 9. Right? This was the original matrix. And now in order to calculate the determinant of A is equal to, take any row or columns of the matrix A and the cofactor. For example, I take the second row. I take the second row of the matrix A as well. So I write them in the form of a vector. Minus 30, I write this one here. Minus 7 and 17. And I write this one in here too. 4, 5, and 6. Now the determinant is to do the inner product of this one. How we were doing the inner product? Recall my note. You multiply each element and you sum all of these. So it will be minus 13 times 4 plus minus 7 times 5 plus 17 times 6. So the result is going to be 15. So the determinant of matrix A is 15. Now there is a very cool things in here. It's a mathematical, very cool things. If you take any row, if you take for example another row or another column, let's say I take this column and also this column, and I do the same inner product here, you will get the same result of 15. Isn't it interesting? See? We are surprised. But this is mathematics, so it's going to be very beautiful. Now, you may ask me, okay, we found the determinant of a matrix, so now what is going to do with the inverse matrix? How we can find the inverse matrix? Be patient. I need to introduce one more matrix to find the inverse matrix. Now that's where we have to define cofactor, adjoint matrix, sorry. Adjoint matrix. So the adjoint of a matrix A is written as, you know, the theta A. I know that theta is the cofactor matrix. And I take the transpose. So the adjoint matrix is simply the transpose of the cofactor matrix. So remember here in our case, this was the cofactor matrix, right? This is the this was the cofactor matrix. How we can take the transpose? Let's write it down again here and take the transpose. The theta A was, what was the theta A? Is 3, 12, minus 12, minus 13, minus 7, 17, 8, 2, and minus 7. Now the adjoint of A is simply the transpose. How we were taking the transpose, remember, we were doing it like this. We were taking the first row of the matrix and we were writing it as a column. 3, 12, minus 12. Now we do it for the second row as well and write it as the second column. Minus 13, minus 7, and 17. And the last column here is 8, 2, and minus 7. So this is the adjoint matrix. Very simple. If you have the cofactor matrix, you can just easily do the transposition and find the adjoint matrix. Okay? Now we are at the final destinations and you are impatiently waiting that how we can calculate the inverse of a matrix. Now I'm gonna reveal that secret to you. Now that you know all these matrices, I tell you that the secret is A minus 1 is equal to 1 over determinant of A times the adjoint matrix of A. Isn't it cool? Right? This is very cool. So now keep in mind this formula. So now recall the matrix A that we had it before. Okay? So now recall the matrix A that we had it. If for that matrix we know the inverse is gonna be 1 over determinant. What was the determinant? 15, right? I know that one. And times the adjoint matrix. I just need this one here. Right? I just need that one here. So I need to write it as 3 minus 13, 8, 12, minus 7 and 2, minus 12, 17 and 7. Yeah, that is the inverse of matrix A. We found it. Congratulations. Now, as a practice for you, you have the matrix A1, A minus 1 in here. Prove that the A, you have the matrix A. Prove that A times A minus 1 is equal to 1, 1, 1, 0, 0, 0, 0, 0, 0. Prove this at your home. You're right now at home and you have a lot of time. So just try this one. A times A minus 1 is identity matrix. So we simply call this one as I3, which is, we say that the order of the A, because the identity matrix is on a square matrix, so it's of order of 3, means 3 by 3 matrix. Don't forget, please, prove this one and prove yourself that mathematics is true. Now I'm gonna give you a very cool definitions. I told you, I guess, previously about diagonal matrix. A diagonal matrix. A diagonal matrix is a matrix that the element of the diagonal, this is the diagonal, it's a diagonal is an S square matrix. So this is the diagonal of the matrix. All the elements except on the diagonal are 0. 0, 0, 0, 0 everywhere. 0, 0, 0, 0 everywhere. Okay? And the element of the diagonal is non-zero. Okay? This is a diagonal matrix. Let me give you an example. For example, matrix A is equal to 2, 3, 4, 0, 0, 0, 0, 0, 0 is a diagonal matrix. Why? Because the diagonal is here and all the elements except this one is 0. See? This is a diagonal matrix. Now for a diagonal matrix, you don't have to do all those painful and cumbersome procedures to find the inverse matrix. So what we can do is very simple. The A minus 1 for a diagonal matrix is equal to, it's a diagonal matrix. So I know that these are going to be 0, 0, 0, 0. But on the diagonal, it's very cool that you inverse the diagonal. Here is 2, you inverse it, write it here. 1 over 2. Here we have 3, you inverse it, write 1 over 3. And this one is 4, you write 1 over 4. It's very cool. And just try this one at home again for this one. Prove that this matrix for here, A times A minus 1 is again I3. Prove this one at home. Okay? Cool. Now we are gonna define something. A singular matrix. So we have a new definition of a singular matrix. Singular matrix. What is a singular matrix? A singular matrix is a matrix that the determinant is 0. So the singular matrix is the determinant is equal to 0. If the determinant is not equal to 0, we call the matrix is non-singular, or the matrix is full rank. Okay, this is important. So if you have a matrix that the determinant of that matrix is 0, so your matrix is singular. Okay, you will understand why we call this singular later. Now let's have some cool properties of inverse matrices. Inverse matrix. We all know the first one. You all know A times A minus 1 is equal to A minus 1 times A, and all of them is equal to I. Identity matrix. This is the first properties. The second one, A must be square matrix. We are reviewing. if the A wants to have an inverse, A must be a square. M by N. M matrix. I'm sorry. If you are a 2 by 3 or if you are the 4 by 3 matrix, I'm really sorry to say that there is no inverse for you. How poor you are, right? Okay, so sometimes it's like this, I don't know. There is no inverse for those matrices, and they need to cry. The third fact or properties. What is the third one? Okay. If you take the inverse of matrix and then take an inverse of the inverse, guess what? You're gonna get A, the same. Okay? You're gonna get the original matrix. It seems very obvious, but there is a proof for that one. And I'm gonna ask you as a practice to prove this one. Prove it. Prove it, okay? But the proof is simple. I just want to show you very simple things here. Let's say the A minus 1 is B. Let's say the A minus 1, for example. I'm going to prove this one. Very simple. Let's try. Let's say the A minus 1 is B. And then this equation, let's say B minus 1 is equal to a matrix C. I don't know what is that. Okay. Now I multiply each time by B. So the B times B minus 1 is going to be equal to B times C. I know that B times B minus 1 is I. Right? So now from here I know that B times C is equal to I. I'm in search of matrix C, right? I want the matrix C. So now I multiply both sides by B minus 1. So it will be like B minus 1 B times C is equal to B minus 1 times I. B minus 1B is going to be I, and I times C is going to be C. In here also, B minus 1 I is going to be B minus 1. Did we get anything? No, we didn't get anything. Okay, so you prove this one, okay? But this is the procedure. I mean, to prove that equation, this is the procedure that you can go by defining this one, by multiplying that one, okay? Let's go to the other fact. Now the next fact is this one. Do you remember for the transpose matrix A times B transpose was equal to B transpose A transpose, right? It's the same for inverse. A times B inverse is equal to B inverse A inverse. Don't forget that one. And the last properties, which is very cool, is here. It's very cool. If you take transpose of A and then take the inverse, it's the same as if you first take the inverse and they take the transpose. Prove this one. Okay, it's gonna be cool. It's very, working with matrices is very cool. I really invite you to do that. So far so good. Do you have any question? Of course not, because you can't ask your question right now. So we continue. Now we are at the end of the systems, at the end of the lecture, and the last things and the most important things that about the matrices is this system of equations. If you remember the high school, we were, for example, equations, system of equation, two equations like 2x plus 5y, for example, is equal to 1, and x minus y is equal to 2, right? How we were solving this one? We were solving these equations like this. We were saying that, for example, multiply the second equation by 2, by minus 2, so it's going to be minus 2x plus 2y is equal to minus 4, right? And then we said that take the first equation and multiply and sum with these equations. So we are eliminating the x. So 2x minus 2 is going to be 0, so it's going to be 7y is equal to 1 minus 4, it's minus 3, and then we say y is equal to minus 3 over 7, right? And then we were putting this y into these equations, and then we were finding the x. This is very cool and simple for two equations with two unknowns. But what if we have more equations, like we have a 3 by 3 equations? Let's say we have an equation like x plus 2y plus z is equal to 3, 3x minus y minus 3z is equal to minus 1, and 2x plus 3y plus z is equal to 4. So it's the 3 by 3, it's a 3 equation, 3 unknowns equation, right? How we can solve this one? I want to give you a very simple how we can use matrices to solve these equations. So you write like this, you make a matrix like this one, you make another matrix is equal to, so what we do in here, we put the variable which is the x, y and z in here, x, y and z, right? And then we put all the coefficients as a matrix. You see these coefficients in here as a matrix, so it's gonna be 1, 2, 1, 3, minus 1, minus 3, 2, 3, 1. And then you take the answers as a vector column and you put it here, 3, minus 1, and 4. Now see, we have a system of equation in matrix form. We call this one as the matrix A, which is the coefficient matrix. We call this one as the X, which is the unknown matrices. And we call this one as B, which is the answer matrix, the known matrix. So the form of this equation is A times X is equal to B. Okay? Now we know how to find X, right? It's simple. Multiply both sides by A minus 1. And then we are going to get A minus 1, A times X is equal to A minus 1, B. Right? And then we know A minus 1A is I, and I times X is X. So the X, we found the X, we are very happy. X is A minus 1B. Very happy, right? Okay, let's have an example here. Let's have the example above. So we know the matrix A. We can find the inverse of this matrix I just told you, right? So now we know how to find the matrix. We first find the cofactor, and then we find the determinant from the cofactor, and then we find the adjoint matrix, and then 1 over determinant times adjoint is going to be the inverse of A. Now there is a condition here we are going to discuss a little. Remember that the inverse of A was 1 over determinant of A times the adjoint. Now I'm going to ask you the question, what if the A is a singular matrix, which means the determinant is going to be 0. So when the determinant is 0, 1 over determinant, it's going to be undetermined, right? It's undetermined, so there is no inverse matrix. Cannot be determined, right? So now we know, for a system of equation, if the determinant of the coefficient matrix is equal to 0, then we say the system is underdetermined. Which means that either there is no answer for it, or there is many, which we don't know. So the point is there is not a unique answer. Okay? Cool. Thank you so much for your listening, and I hope you a very happy life in your home. I will prepare you some homeworks and you will answer. Thank you and stay safe.